yeah, let's talk a little bit about building. Sorry for this slide, this doesn't look pretty. So let's talk a little bit about how do you build models. So when you build models, let us just concentrate on the experimentation part. So when you build models, it's very important that you keep track of stuff like how is your model. You have to have, first of all, you have to have a way to evaluate your model. You have to know how is it performing and what are your criteria for how good a model is something you have to define. There are hundreds of ways to define or millions of ways to define what you mean by a good model. And this has to be deeply and more connected to the business value you can get when you decide on which metric to use there, the better. So you have to have something that makes sense in a business perspective. And then you have to keep track of all this evaluation, because mostly when you build a model, you can be doing tens, hundreds of evaluations, and you want to go back and you have to look, oh, I used a little bit different data there, and I've changed that data a little bit that time, and I get a little bit better score in this kind of metric, a little bit worse in this metric. And that's a hugely time demanding kind of thing, and you forget, oh, was actually a really good model, but I forgot how I built it. So you have to have some kind of automated way that takes care of once you run a model and you have a lot of PDF, you have a lot of metrics, you have scores, and you have some pictures and graph. It just dumps it and takes care of storing that. So you can look at, the experiment number 240 was the one I wanted. I have this kind of parameters. I have this kind of model setup. I have this kind of data setup. And then when you finally picked out a good performing model, you have to store it. So you have to have somewhere that actually, because there's a difference between experiments and model. The model is the one that goes into to production, but that model also need to be version control. Like it has to be, maybe you updated it, or maybe you change some parameters in the next quarter. You have to also have kind of understanding of what happened there. So that's the important part. Okay, let's move on to machine learning, a little bit more juicy stuff. It gets down to some technical, a little bit technical. I don't know how. Have you any of you built models before? Then this is probably too low, too easy. But I will try to just talk a little bit about it from a very simple perspective. So imagine you having, you want to predict something, whatever it is, the height of a person, given some attributes. So x1, x2, x3, and whatever, they are attributes that come into the model. That could be your height, sex, age, and so forth. And then if you disregard that layer 2, you just have x1, x2, x3, and you have and then those numbers have a scaling. So that's what the model do. It tries to find the factor that goes in front of x1. So we have a1. That's a bad example because a1 is there. But you have, let's see, y1 that is scaling the x1. So you can think of height is 3 times your age, for example. That's a very bad model, but it could work. Let's say it's just that. So we scale it to 3. So that's the model's job. What is the good scale for each parameter here? And if you only have one layer, you only get a simple model. In most cases, you could do something that makes it nonlinear, but just disregard it. In most cases, it's just a linear. So it's a times x, or b times x. But once you add another layer, let's say this x1 goes scale, this scale x1 goes to the next layer, and it gets scaled again. then you're starting to get more complex stuff. But then you're also starting to get, how do I actually solve this equation? Because it's an equation that needs to be optimized. It needs to be minimized or maximized depending on your goal. So you have to have, at the end, you have to have some kind of goal, like the final A3. How close is it to my actual answer? So then you have a metric. That's a mathematical function that tells you how close is it. In most cases, it is just the final answer minus the real answer squared. And the reason for that is mostly because it's easy to take the derivative. Because you want to see how quickly this is moving. You have to see how is your suggestion or your model, how is it moving towards the answer or away from it, and how fast? If you're moving away from the answer, you're definitely in a wrong spot. Then you have to do something. So that's what you do. You look at the derivative. The derivative of a function tells you how fast it's growing. So you look at how fast it's growing and in which direction. It gives you a vector, a direction and a amplitude. And then you want to scale this. So you have to adjust by this factor. So you go back by each step. You use the chain derivation. It's just a mathematical, quite basic thing. You just end up with the derivative. You move each layer backwards. That's called backpropagation. And it's a very important thing in neural networks. Okay, let's look at this in actually a very simple way, and this is not a way you should use PyTorch, but look at PyTorch, because PyTorch, I don't know if anyone used that before or heard about it, but that's just a way to do optimization, including stochastic optimization, but just think about it as optimization with the GPU, or that's a big part of it at least, because all that's why NVIDIA has such a huge spike in the price lately, been becoming one of the third $1 trillion company. You've probably seen. The huge part of that is because GPUs were used for gaming, and they're basically just matrix multiplications or matrix operations. It's just adding a number to another number. That's what they do. They're really good at that, but they're really bad at other stuff. Like CPU is really good at everything, but the GPU is very good at just adding two numbers together. And a little bit more, but just think about it like that. They're really good at it. And that's very important in machine learning. And so NVIDIA is positioned as one of the huge players in machine learning because of it. So here we are, Torch, and so what Torch do is just basically take a vector, just a list of numbers, and give it to the GPU. I'm working on the CPUs now because that's just simpler. But for me now, I'm on a laptop, so don't worry about that. But you basically want to work on the GPU. And this line, I create some fake data. So the data looks like this. It's a tensor, and you see it's a p number p, or in the space of p, all the numbers from minus 3.14, 16 something, to plus 3.14. And then y, if you want to see y, we just do a transformation, and we do a sinus transformation. This won't probably tell you anything, but it basically looks like this. And we want to model this. And we want to create a model that does it. I'm telling it how quickly do you want to learn. So I'm telling it you want to not too fast. And then I do a loop. And this is the model that I'm building. So we want to predict the sinus curve from x. So given a number here, like -1, we want to have something like minus 0.75. Clear? So that's what, and we want to do it by having this just a constant, a number, plus another number times with x, another number times with x squared, and then another number times with x cubed. So basically, if you remember back to your calculus days, the sinus curve could be approximated with enough of those. That's a very famous thing in mathematics. You break down a function into simpler functions. And the sinus curve is a complex function, but it could be written as a function, as a sum of a times x to the power n, and you add those all up. But you have to have n go to infinity to be perfect. So we don't have that. We only have 3. But we have the power 3. And this is our loss sum, as I talked about. We do the difference between the predictions and the actual solution, or the real solution. And then we do it to powers of 2. And then we calculate how fast is this solution growing. We do that by the derivative, and the derivative is just 2 times the difference. Okay, so this is a gradient. And then we update all the parameters by the learning times the learning rate. So then in these new numbers, we can update them. So minus, we do the number minus something. Then we run this, and it should be perfect. Oh, it is not fine. After we do this one, so with that, yes. Here we can see the how far we are away, the penalty.
I'm sorry,
So
but
it's
your
really high, and it goes down until 9. And 9 is good enough because we can't get it, the whole thing. It's too, we can't approximate. We can approximate it, but it can't be a perfect approximation. If you want to have an approximation that's less, the difference is less than lambda, then you have to maybe increase the n, or depending on the difference, epsilon. The difference epsilon, you get different and kind of how many sums you have to have. So this is probably pretty close to the optimal solution, given that we only have 3 or 4 parts. And this is the plot of the solution. It looks pretty good. And this is the actual solution. You can't see that much, but you can see this one doesn't, around here, it goes a little bit faster to 0. So, but this one doesn't, it's not as steep. But it's a really good approximation. So that's basically it. That's how we do machine learning on a GPU. How we did on CPUD, but also GPU. You basically just let it run, and it runs for days, optimizing those parameters for that model we built. So the important part is the model and the loss function. And then PyTorch or TensorFlow, which that's one of the popular libraries, do the rest.
How would it be like if we keep a more real life example? Like, let's say you have a model, like a friend of mine is a labor union guy. He had this idea: let's make a model that predicts who will be sick, because he works a lot with sick leave in the company. Then you would have a person, right, with some attributes. He is a farmer. He is this age. He is from this family, maybe a bad family. Just throwing crazy ideas here, right? And then you can start predict the probability he will call in sick.
Yeah, and it will basically be like this. So instead of having, I probably can't. So let's say we have a y prediction here. Caps lock. Y pred equal to, instead of having this squared, let's say, then you probably have a correction parameters like a, and we want to guess we want to guess a number between 0 and 1. That makes it a little bit complicated, so just ignore that for now. if we do like b times x 1, for example, that would probably not be a number. We can't guarantee that, but a number between 0 and 1, so we have to scale it because we want to predict the probability of not calling in. But forget about that. Let's get a number. The higher the number is, the higher the that's linked to the higher probability. Then you have something called a link function that actually does that for you. But we don't want to go into that. So then you do like this. You have this b. That's the one you want to optimize. Times the parameter 1. That's what did you say if it's a farmer or not? All right. And then you have c. Let's call this a1, a2, a3 times some other variable x2. And this is a really simple model. And this is probably like there have to be some number that just makes it all come together. That's the a. So don't worry too much about that. Let's say about again back to the height. For example, if you want to predict the height just from the age and sex will be 0, 1, then the height height from the age could be corrected by this number. And then you can make more complicated model by doing this one. This is ypred. Then you can take ypred 2 equals, let's say this is a vector instead. Okay, we can just type ypred is equal to another number set times that. So we can continue going, making another layer here. That's how we make that's called a deep neural network, when you have a lot of layers. But this is basically how we do that. Is that clear, Thomas?
I'm learning and contesting. I'm going to watch this a couple of times to get into the way. It's interesting.
Yeah, it's if you haven't worked with this before, it's very much terminology and a lot of symbols and a lot of stuff. So don't worry too much. But it's basically just finding the parameters that, let's say again with the height. If your height is 180 and your age is 50, yeah, I maybe multiply it with 3, and then I add 30 or something, and then maybe do a correction for age. That's my model. If I only want to model based on, or let's say the case when your probability of calling in sick will be some factor times if you are a farmer or not. So it's a farmer, you will have a number. If you are, and maybe the age, let's say the age, and then maybe income. So then you have some factor times the age, and then some factor times your income. But then maybe you want to scale those kind of things first. Maybe income should be in buckets instead, and yeah, it all gets very complicated very fast.